In this video, we're going to look at an example of calculating an average energy given a partition function. We're actually going to derive this expression for the partition function of a monatomic ideal gas. And actually at the end of this chapter, we'll look at why big Q looks like this. But this expression over here for little q we'll derive in our next chapter. And see where this comes from. So this isn't just something out of thin air. But just to show you an example of like how we can use this equation for the average energy, right? So remember, our average energy is equal to negative of this derivative of the partition function with respect to beta, holding n and v constant. Okay, so since we're going to need to look at the natural log of q, let's go ahead and write that out. ln q, all right, that's going to be equal to ln little q to the n divided by n factorial, which is equal to n log little q minus natural log of n factorial. Okay, so the thing to remember here is that our derivative is only with respect to beta. So the only terms we actually care about are the ones that have beta in them. So while this partition function is complicated, it has all these extra terms, we really only care about things that have beta in them. All the other terms, when we take the derivative, are going to go to 0. All right, so we need to go ahead and plug in what is q, our little q. So natural log of q is equal to n times the natural log of this 2 pi m over h squared beta to the 3 halves times volume minus log of n factorial. One thing we can already see that this term has no beta in it, so we're not going to need to worry about it. But since this is all inside of the natural log, we can go ahead and break this up into multiple terms and only keep the ones that have beta in them. All right, so if we do this, we will get a minus 3n over 2. So that comes from, our n comes from here. Let me do that in a different color. The n comes from here. The 3 halves comes from this power here that's going to multiply times the natural log. And the negative sign comes from the fact that our beta is in the denominator. But going to get minus 3n over 2 natural log of beta. We'll have a separate term that is 3n over 2 times everything else. Right, so we'll have our natural log of everything else, 2 pi m h squared v. So that's just lumping together all of the things that don't have beta in them. And we still have our log of n factorial term. But this, I'll put it in red, this is the only term with beta. And since we're taking the derivative with respect to beta, when we take the derivative of this, all these other terms are just going to disappear. So when we write out d log q d beta, right, we need the negative of that. Oh, sorry. We'll do it without the negative sign, then we'll remember that there's a negative sign in the original energy equation, holding n and v constant. And that's key, is that that's the reason all these other terms are constant and will disappear. If n and v were not constant, then this wouldn't work out. But we're going to get minus 3n over 2 d log beta d beta. So we take the derivative of the natural log of beta. And then these terms over here, when we take the derivative with respect to beta, they're all going to go to 0. So we can ignore them. All right, and that'll give us minus 3n over 2. The natural log, the derivative of the natural log is equal to 1 over. So the derivative of the natural log of beta is equal to 1 over beta. And we've seen the opposite of that. Doing the integral of 1 over something is the natural log. We're taking the derivative this time. And then we can plug in the definition of beta is 1 over kBt. That gives us minus 3 halves times n kBt. All right, so since that's our derivative, then the average energy is the negative of that, which is positive 3 halves n kBt. But as I've mentioned before, KB times Avogadro's number is equal to R, so we can also rewrite this as 3/2 times N, number of moles, RT. And this is what's observed experimentally. This is the average energy of a monatomic ideal gas. And so what we can say is that what we postulate is that when we have a big enough ensemble, we have a large ensemble, we would say that when we're looking at a lot of particles, the average energy that we calculate here is what we're going to see, is what we're going to observe. Oh, sorry, that shouldn't have average brackets on it. But if we're looking at a big enough system of particles, our average energy is what we're going to observe. And so this is an example of how we can do a calculation with a partition function to find an average energy.